All right. We start chapter 4. Chapter 4 is, like I said, a switch from chapters 3 and everything before, where we used derivatives before. We're going to be using something different, chapters 4 and 5, which is going to end our course. In chapter 4, we discussed the second of the two main problems in calculus. The first main problem in calculus, where we spent the majority of our class, I mean more than half of it, was can you find the slope of a curve at a point? What was that? Just derivative. The second question in calculus wasn't about the slope of a curve at a point. It was, can you find the area under a curve? Do you remember that question? I introduced it, I think, like the first day of real calculus. I said, can we do this? Given some sort of continuous function from A to B, can you find out what the area is between that curve and the x-axis, or basically the area under the curve, from here to here? And the answer is yeah. Yeah, and we actually have two ways to do it. I'm going to introduce to you what's called the rectangular method today. We'll deal much more with it in section 4.4, 4.3, and 4.4. They're kind of tied together on how to actually do this with the rectangular method, but I'm going to introduce it to you today. And then we'll talk about what's called the antiderivative method, which is a more concise way to do it. Are you ready for it? So this, I'm going to kind of go in a weird loop. I'm going to introduce this with the rectangular method. We'll talk about antiderivatives, then I'll use rectangular method to kind of prove what we just learned about antiderivatives. You follow me? So we have to wait till 4.3 to prove some of the stuff I'm talking about here today. I'm going to give you kind of an intuitive approach on it, though. Hopefully it makes sense for you. So first method, let's talk about the rectangular method and at least the idea behind it. So rectangle method. Rectangle method says, well, why don't you divide your interval into n, some number, n, equal subsections, equal as far as their width goes. Subsections, subintervals, whatever you want to call it. And create a rectangle in each subinterval, in each subsection. Hence where we get the term rectangle method, or rectangular method. So here's basically the idea. Let me redraw the picture for you. Let's say that I make this a little bit bigger too. Here's my graph. Here's my interval. The idea behind the rectangle method is, can you find the area under this curve the way it is? No, not really, because we don't have a formula for this, and even if we did, it doesn't have straight sides, and the only way we know how to take the area up till right now in geometry is if a figure has straight sides, right? Whether we can break it up into rectangles or triangles, because we know how to take the areas of those figures, or perfect circles, you know how to take the areas of those figures. This is not a regular shape that we know of. It's just some random function. In fact, I haven't even been specific. It could be any function. But the idea is, let's go ahead, let's break this up. We'll say, okay, we're going to split this up into however many parts we choose. Let's just assume those are equal widths. That's about right. And says if we have some sections here, what we're going to do in each section, since they have equal widths, so I'll tell you why we need equal widths later on in section 4.3, 4.4. But right now, let's just assume we have some equal widths. So our bases are all the same. Our rectangles, equal bases means they're easy to add together. That's basically it. So for each interval, subinterval, let's make a rectangle. Now there are several ways to do this. I'll show you one way. The problem is now, you got to determine how you're going to have the height of our rectangle. So one way to do this is to use what's called left endpoints, another way is to use right endpoints, and the third way is to use midpoints. And here's what that means. You go to the right endpoint of your interval. Here's my interval. I go to the right endpoint. I'd say I'm going to go up to where that touches my figure. Does that make sense to you? A left endpoint would say I'm going to go up to where my left point touches my rectangle. A midpoint would say go to the middle, see where that touches the figure, and then make your rectangle. That would determine your height. So we have left endpoints, where that touches. Right endpoints, where that touches, or midpoints. Let me show you the midpoints, and here's how you do it. Okay, from my midpoint, I'd go up here, where it touches that f of x, wherever my function is, that's where I cut it off, and that makes my rectangle. Does that make sense to you? Why do that? Well, it's actually not going to matter when we finish 4.4. We'll talk about what's called the definite integral. It doesn't matter whether you use left, right, or center. But for us, if we are always using one endpoint, sometimes we can systematically over or underestimate the area, and that would be a problem for us. Then this one would go, okay, let's go up. Where that touches, I'll draw the top of my rectangle, finish it off. And you would do this for every interval that you have. How many people feel okay about the idea here, the idea of drawing rectangles there? Do you see where the midpoints come into play here? The midpoint gives us the height of our rectangle. That's going to be useful when we get down to 4.3 and 4.4. Very useful. Now, how would I find the area of this figure, the approximation of this area? What would I do with this? If we know the area of a rectangle, which we do, right? A rectangle is just a geometrical figure. If I can find this area, and this area, and this area, and this, if I can find all the areas of all my rectangles, all I have to do is add them together, and I'm going to get at least an approximation of the area of my figure. You follow me? Now, is it going to be exact? Well, you can tell it's not. I mean, sometimes I've overestimated, sometimes I've left out some area. Sometimes it's about right, but sometimes, and I don't know whether I'm perfect or not. So I'm not going to be exactly right. It'd be a miracle if it was exactly right. It's not going to be a miracle. This isn't Harry Potter mathematics, so magic doesn't happen in math sometimes. But anyway, that's another topic, I suppose. It's not going to be exact. It's going to be an approximation. Now the question is, how can I make this better? So would you agree that the more rectangles I have, the better approximation this will be? So, I mean, here I had 1, 2, 3, 4, 5. I had 6 rectangles. If I had 100 rectangles for the same width, 100 rectangles mashed up in there, I'm going to over and underestimate by a less margin, lesser of a margin, right? So the more rectangles I have, the better approximation becomes. So as the number of rectangles n goes to infinity, or as the space between the rectangles goes to 0, right? Does that make sense? If there's a space, as this goes really, really close to 0, that's the idea of a limit. As that goes to 0, then I have a very, very good approximation. In fact, it's so good that it's exact. So the idea here is cut your region into rectangles. Every rectangle, you're going to take the area of that. Add all the rectangles together, and you're going to get a good approximation of your figure. How do I make it better? You let the number of rectangles go to infinity. The way you do that is let the space between them go to 0. For a better approximation, make the space between each interval Notice that in this context, the space between each interval, that's the width of a rectangle. Approach 0. And again, the idea is, well, think about it. If you have a finite distance, a to b, and you let the distance of each subinterval go to 0, how many rectangles are you going to have? If you have a finite space and you let the distance between here and here go to 0, you can pack in an infinite number of rectangles, right? If you pack in an infinite number of rectangles, you will have no over or underestimate. It'll basically be like finding the area under a distinct point, which is impossible. You can't do that. But if you say it's really, really, really small, and you can put a paper between it, then it'll be exact. And that's the idea. That's the limiting factor. Same it's kind of basic concept of a derivative, right? We took the distance and made it 0, and we're taking the distance and making it 0. Very similar idea. Only now we're talking about an area instead of a slope. How many people understood the idea of this? Good. Good. That's fantastic. More on this in section 4.3 and 4.4. This is all you get for right now. Just a little taste. This is appetizer. Are you satisfied? No, of course you're not. That's why you need more of a meal. This is the meal. Okay? Different method. Antiderivative method.
Practice that line over there.
No, I just made it off the top of my head. Pretty good, huh?
Nice. Improv.
I suppose if that's the appetizer, this is like the salad and the main course, and we tie it all together with the dessert. And then the chapter 5 is icing on the cake, baby. Just how to use it. If you like cake.
Insert your favorite dessert here.
You don't put icing on creme brulee. Burn it. You do, burn it. Anyway, antiderivative method. This I'm going to go a little bit past where the book takes you. The book has you do just what antiderivatives, how to do antiderivatives. What I'm going to do is tell you what an antiderivative stands for and then how to do them. You're going to find out now, I'm going to prove this to you after we do 4.3 and 4.4, so I'm going a little bit beyond. That if a of x, here's kind of the special deal, here's what you find out, the end game of section 4.4 is this basically. If a of x stands for the area under a curve, for some function, if a of x is the area function for some f of x, some curve like this for f of x, on some interval. I've got to give you an interval, otherwise you can't find an area. Does that make sense? You have to have an interval. Areas are a definite thing. We'll talk about definite integrals later on, but areas are definite. You have to have points and numbers. Then here's what I'm going to tell you. It's kind of a very cool thing. This is where we're going to end up. Again, I've said it 5 times now. This is where we're going to end up after section 4.3 and 4.4. You get it? We're going to end up with this statement. Which is a fantastically marvelous statement. It's magical right now because you don't know the concept behind it, but it's magical. What it says is, this thing right here is an area. This thing is an area, right? It says if you take, this is kind of crazy to think about, but if you take the derivative, that stands for derivative, right? If you take the derivative of your area function, it will give you your original function. It will give you the line, the curve. So basically it says this. If your area function represents the area, take a derivative and you get the function back. Does that make sense to you? It shouldn't really, not that much. I'm going to prove this to you later. I'm not proving it yet. What you need to know right now is that if you are given an area function, take a derivative of that thing and it will give you your function back. Well, now that's cool, but we're never going to start with this. We're always going to start with our line, right? That's what we want to get to. So, well, this implies this thing. This says if we want to find the area under a certain function, we basically need to be able to undo this. We need to undo a derivative. For some interval, let me go through this one time for you so you kind of get the interplay here. Here's what it says. It says the area of a curve is a of x. What I know for sure is if I take the first derivative of the area, that's equivalent to my curve itself. So if I want to find the area under my curve, this statement's true, right? The first derivative of the area is the function. So if I want to find the area of the curve, under the curve, what I'm going to do is undo the derivative that gives me the area. So basically here's the idea. You pretend that your function is a derivative. If you undo that thing and treat it like a derivative, you're going to find what's called the antiderivative. That is the area under the curve. That's the idea of the antiderivative method. We'll get more into it in a second. I'll prove it to you. I'll prove it with an example. I have to prove it to you with 4.3 and 4.4 later on. I'll prove it with a couple examples. So if we're going to find the area under the curve, under f of x, we must undo a prime of x to find a of x, the area. Would you like an example that you can actually kind of see?
Mm-hmm.
I was hoping you'd say that. Have I lost you yet?
No, halfway.
You get this, right?
Yes.
Oh, good, good. Now, this is not what we're talking about today, so it's good for 4.3. Do you get this? No, you don't yet. Trust me, you don't. You won't get it fully until 4.3 or 4.4. The idea is, can you find an antiderivative? I'm going to teach you that in a second, but I want you to understand the concept behind it as well. The concept is we're trying to find the area under a curve. That's why I gave you this introduction. That's the idea, so I'm trying to get that in your head. Remember how I always kept saying, what's a derivative? What's a derivative? And you're like, oh my gosh, slope of a curve at point. You know that, right? Good, because I pounded it in your head, and that's going to do the same thing here. What we're doing is we're finding the area under a curve. That's what an antiderivative is. What I've told you, and I've done it without proof, I'm not going to prove it till later, I've told you this. I said the first derivative of your area is your function. So if I can undo my function by treating it as a derivative, I will find the area function. So basically we need to go backwards from a derivative. Did you get that? If the function is the first derivative of the area, that's what that says, the function is the first derivative of the area, if I can undo the derivative, I get my area. That's the idea. That's the antiderivative method in a nutshell. A very quick statement. Now, let me do some of this with geometry to show you that it does in fact work. Then we'll get on into some antiderivatives and how to do those things. So, example. If we have a function f of x equals x plus 1, I'll give you something easy to graph because I'm going to show you the graph in a second. I want us to find the formula for the area on 1 to x. Now, this would kind of be stupid if I give you just 1 to 3 because we could just use the triangle and find the area. But what I want to find is 1 to x, and I'll show you why this works according to that. First off, can you graph this? Geez, I hope so. What's your y-intercept? What's your slope? Would you agree that that is your function? We're trying to find the area of that between, what did I say, -1? Oh, you know what? I want -1. Let's make that negative much more interesting. -1 to x. Now I don't know where x is. I made it positive, but it doesn't have to be positive. What we're talking about, wherever this x is the area of that shaded region. Now, keep in mind that this function is x plus 1. What shape is that? Can you find the area of a triangle?
Yes.
Of course you can, yes. Let's find the area of a triangle. The area, in terms of x, notice I'm using the same terminology I used over here, right? That's an area function. The area in terms of x, wherever x happens to be, is. How do you find the area of a triangle again?
1/2 base times height.
Very good. 1/2 base times height. So I'm going to write 1/2 base height. So that would be 1/2. Oh my gosh, what's the base? Oh, let's think about that. What's the base? Is the base x?
It's not x minus
X minus 1. Oh, we're close.
-1 plus.
How do you find the distance between 2 points? Between two numbers?
Subtract.
You subtract them. You subtract the numbers, right? You subtract them.
X
So
plus 1.
this would be, the distance between here and here is x minus, not 1, not 1. This would be, the distance between here and here would be x minus 1, right? There's going to be a difference here. So it'd be x minus negative 1. Yeah, that's x plus 1. Do you see where we're getting the x plus 1? Well, I mean, you can see it. You can just see it on the graph, really, just intuitively. This distance is x, right? Yes? That's one more unit. That's x plus 1. Not x minus 1. That would be over here. So we have x plus 1. So 1/2, okay, that's x plus 1. Okay. Oh my gosh, what's the height? What's the height? F, okay, f of,
X plus 1. X
Not
plus
quite.
h of 1.
no h's. We don't want any h's. You're thinking, I like the thoughts. I like good thinking, you have good thoughts. None of them happen to be right now, but that's okay, all right? Tell me something. If this was a 3, if that was a 3, what would the height be? Very good. If this was a 7, what would the height be? 8. You all see the 8. If this is an x, what is the height? X plus 1. You're taking the number, you're adding 1 to it. That's what the height is. So this height, whatever this x is, right? It doesn't even matter. If it's here, if it's a 1, then it's 1 plus 1, it's 2. So this height, x plus 1. You okay on the height of x plus 1? The function says the height, right? That's what the function means. So take the value is x, plug it into the function. If I plug in x, I just get x plus 1. That's what we do. We don't plug it in and get x squared. That's not what we do. We're not squaring the number and then adding 1. We're just plugging the number in. I said if that's a 3, you get 3 plus 1. If that was a 7, you get 7 plus 1. If that's an x, you get x plus 1, whatever it is, plus 1. How many people understand? Raise your hand if you feel okay with that. Good. Then our height is also x plus 1. You okay with this so far? I'm just kind of proving this for you with an example. It's not a genuine proof, but I'm showing you that it does work. If I distribute this, I'm going to get, let's see, 1/2. That's x squared plus 2x plus 1. Do you believe me? You should, because that's right. Come on now. If I distribute the 1/2 even further, I get x squared over 2 plus x plus 1/2. You follow me with that so far? Okay. Now here's a cool deal. Would you agree that whatever I tell you for x, you could find the area of that triangle? If I said x is 9, could you find the area of the triangle? Yes, you could. You just plug in 9. This is, in fact, our area function because we made it up geometrically. It's just the base times the height divided by 2. That's all we've done. So far, so good? Now, what I want you to do is do some magic. This is the area function. I want you to take a first derivative of that. Would you do that for me? hope you got magic. Hope so. It's just not that great magic. I would have told you it was going to happen. But what's the first derivative of A? And that we denote that A prime, right? That's the first derivative of A. What's this? X. Very good, because you bring the 2 down, the 2's simplify, you get X. What's this?
1.
What's this?
0.
Aha! Does that look familiar? Yeah, in fact, this is your function. That's true every time. Right? The derivative of your area is going to give you your function every time. That's going to happen. That's just basically one example showing that this is true for this example. Now, it doesn't prove it at length. I will do that later. But it shows you that you can do it. Shall we do one more? Would you like to see one more? Okay. I'm going to kind of start simplifying this a little bit. Okay. You know what x squared looks like, right? Okay, now this is only between 0 and 1, so I'm not going to draw the left side of this. I'm just going to draw that. Do y'all see that that's the area we're talking about right there? Yeah, no? Is that a triangle? Is it an exact triangle?
No.
Okay. So we can't do the same thing, but we're going to use the idea. The idea is, here's the idea. If f of x equals x squared, and f of x also equals the first derivative of our area function, you believe that, right?
Mm-hmm.
Then the first derivative of our area function equals x squared. That's a basic substitution. It says if our function's x squared, and we know that a function is equal to the first derivative of its area function. You follow me on that? Then we say, all right, well, if fx is x squared, then x squared equals that. That's our jump there. Can you make the jump? Okay. So basically, we're asking this question. Can you find a function whose derivative is x squared? That's the question you ask. Can you find a function, and you know what we're going to call it? A of x, because that's going to be our area. Can you find a function, a of x, whose derivative is x squared? Let's try a couple. Let's just have some fun and try a couple, all right? We know how to take derivatives pretty easily. Let's try one. Let's try, well, if we use some common sense or some critical thinking, I should say, would you agree that you need a power bigger than 2? Probably, because when you take a derivative, that power decreases by 1, right? So let's try x cubed. Does it work? No, because this is going to give you a prime of x equals 3x squared. Right? That's not going to work.
Divided by 3.
Okay, so we need to get rid of the 3 somehow. So if I can somehow undo the divide by 3, then maybe, oh, let's try that. Let's try x cubed over 3. Would that work? Let's try it. If I take the derivative of that thing, what I would do is I'd bring down the 3, right? The 3 and the over 3 are going to be gone. I'm going to get x squared. Okay. Does that work? Yeah, this one, not so much. No. This one, yes, worked. How many will feel okay with that so far? So you're undoing the derivative. You're going backwards. So is it related to a derivative? Absolutely. But you're going the other way. And we had something unique, right? We had to have this over 3 somehow. Now let me ask you another question. It's going to blow your mind up like a mind grenade. What's the derivative of that? What about the 7?
Constant 0.
Oh. There's another one that works. What about this? Very cool, actually. What about that? Any constant. No matter what it is, any constant is going to go away when you take a derivative, right? So what you actually get here is a family of curves. Each of which would work as an area function. So here's what we've done. We've started with this function and we've said, okay, I know the function is actually a first derivative of an area function, whatever that happens to be. So I'm going to set my first derivative of the area function equal to it. I'm going to undo that, treating it like a derivative and undoing a derivative. That's why we call it the antiderivative method. Okay, you're undoing anti, it's opposite of derivative, means derivative, so undoing, opposite of, you're undoing a derivative, that's what we're doing here. Now, unfortunately for us, this is a situation, right? We have we have an infinite number of possibilities for the area function that it could actually be. And in general, that's what you have to put. You have to put that, some of your zone out, you have to put that plus c. The plus c is important. It represents a family of curves, each of which could be the area function. Now, I've also said some specific things about this. I said between 0 and 1, which is going to help us out a little bit, but if I didn't say that, this would be the general area functions of x squared. That's what it would be. You'd have to have more specific information in order to give me an actual verified area. Do you follow me on that? You have to have that. So, do you mind if I go over here? Do you have any questions about this one? Are you with me so far? That there's more than just one of them right now?
Those are the first 3 you actually asked before erasing.
Say what?
You actually asked before erasing.
I know, right? I was polite today. Oops. So a of x equals 1/3 or x cubed over 3 plus c. C is a constant. C is also the y-intercept of a of x. If something's the y-intercept of a function, you should be able to find it by plugging in 0. True? So what this means is that a of 0, if I plug in x equals 0, can you verify that that's going to give me just the c? 0 cubed over 3 is 0 plus c, so it's going to give me c. Now, I don't want to blow your mind up too much, but for this context, do you understand that this area curve is from 0 to x, wherever x is in this case? That's what that stands for. So this interval That interval is 0 to x. This one might throw you for a loop, but I need you to stick with me, okay? If this is the area, from 0 to x, you follow me on that? It's from 0 to x. And we are finding the area from 0 to, what did we plug in for x?
1.
No, we didn't plug in 1. To find this, what do you plug in?
0.
You plug in 0. When you plugged in 0, what's the area from 0 to 0? What's the area? That's basically saying, what's the area of a single point? Can you find the area of a single point? A point is that which has no breadth. So that means you have no width there. So you can't find an area. It's 0 times whatever the height is, but you still get 0. So I know this is kind of awkward to think about the area of a single point, but that's what you're doing here. You're saying, all right, I'm going from 0 to, I plugged in x equals 0. That's how I got this. That's 0. So what this says is, this is basically the area of a single point. When you set x equals 0, your interval is from 0 to 0. That's the area under a single point. The area under a single point is always 0. If you took any statistics at all, you know this. With continuous distributions, if you ask what's the probability of an exact number, it's always 0. Because you can't get it because there's an infinite number of possibilities. That's the same idea. The area is 0. So when you set x equals 0, the interval is 0 to 0. That is the area under a single point. And that's 0. So what this says is, from here, here's what this says. It's 2 parts. Oh, I gotta sneeze. Oh, it didn't come out. Oh, don't you hate that? Were you all ready for it and then nothing? Oh, I hate that.
And then your nose tickles. Like
Yeah, I hate it. Nose tickles. Oh, bummer.
It actually looked like you sneezed for a second.
I tried. I kind of pretended, just so it would look good on camera.
Valiant effort.
Thanks. So here's what this part says. This says if you're going to plug in 0, your area goes from 0 to 0. That's area under a single point. That is 0. This part says, well, I know when I plug in 0 to my function, I get c. Therefore, if a of 0 equals 0 and a of 0 equals c, how much does c equal?
Yeah, 0.
Yeah, that's right. What that says is, though, even though we had the c, we had to take care of the c. The c doesn't always have to be 0. It can be numbers, too. We're talking about initial value problems later on, later on in this section. You might have some c's that are numbers. In this one, you get a 0. So this is what you'd be able to do from this part. After you find your c, you go, okay. Then the area of that curve is x cubed over 3. Now you can start plugging numbers in. Now that you've dealt with the c. On the interval of 0 to 1, the area is, well, let's fill that in. Our area went from 0 to x. Can you tell me what is the x value of our interval there, where we're stopping? You can now plug that in. Now that you don't have that c, you know the c is 0, right? You'd be able to plug in the x of 1. You go, okay, well, then the area that stops at 1 is 1 cubed over 3. Or 1/3 square units. Now that's our idea. Did you follow the idea? I've given it to you in terms of geometry right now. I've showed you some interesting ideas with area to kind of flesh this thing out a little bit. Right now we're going to take a jump away from the actual area. I just wanted to introduce it to you. So it was a very long introduction. Do you understand the introduction? How many people do feel okay with it? So rectangular method is you cut it into rectangles. We'll talk about that later. Antiderivative method is you go, okay, the first derivative of the area is my function. Let's undo a derivative. That gives us an antiderivative. We somehow have to mess around with the c. We have to figure out what c's are. I'll show you better ways to do this as we go on, by the way.
Okay.
Better ways. Yeah, I
I
need you to understand the idea. You need to get the idea. I'll show you some shortcuts and ways to work around that. You follow? But you have to understand the idea. Now we're going to practice most of the rest of our time in this section on how to actually do the antiderivatives. This was fun, but I haven't showed you any techniques on how to do that yet. I've said basically you need to be able to undo it, and we kind of guessed and checked over here. Would you like some better ways to do this?
Yes.
Absolutely. So we're going to start talking about that. This is called the indefinite integral. Indefinite means that I'm not going to give you boundaries yet. I'm not going to give you 0 to 1 yet. That would be a definite integral. That would be the area between the points. That's what we were able to find, right? An actual number. What I'm going to leave you with is how to get down to here, that part. This would be indefinite. It'd say you have a plus c, you don't know where you're stopping, you don't know where you're starting. It's just an indefinite integral because I haven't given you a range of numbers. Therefore, you can't find the definite area. We're just having the function of the area. Do you see the difference there? If you didn't catch what I said, rewind that and repeat that. Some of you get in kind of like weird looks. You don't quite get that. I'm going to just leave you here. I'm not going to give you numbers to start and stop at. I'm going to leave you here, show you how to get this, and later on we'll talk about how to do the whole thing together. So remember, this was an introduction. So indefinite integral means that you're not going to be able to find the area definitely. That's why we call it indefinite. Oh yeah, I guess I should call it, this would be like a subsection. So there's a new word on the board, integral. I'll bring down to what an integral actually is. It's not a hard concept. Given a function, let's call it f. On some interval, let's call it I. I know this doesn't start out so fun right now, okay? It sounds boring. It's not that bad. Just stick with me. Given a function f on some interval I, capital F is called the antiderivative. Please make a note here. This is also the area function. Okay. In general, we call the antiderivative just the capital letter of whatever the function is. So if we have a function f, the antiderivative is capital F. That's all we're saying here. It will stand ultimately for the area function of your curve. Do you follow me on that? That's what it'll stand for. F is called an antiderivative. If this is true. If you can take the first derivative of your capital F, your antiderivative, and it equals your f of x. You'll notice I used the word "and" instead of the word "the." Think back to like 10 seconds ago, maybe like 30 seconds ago, when I said you had a plus c. You can actually almost see it in the purple writing that it doesn't quite erase that well. Remember how we had several, actually an infinite number of functions that you could take a derivative of, and it will give you your original function back again? That's why I say "and." That plus c gives you a whole bunch of them, a whole lot of them. And so what we're doing here is we're saying f. F should be some function that when I take a derivative of it, it gives me my function I'm looking at. That's what happens. That's what an antiderivative is known as. Now, we just talked about it like this. Right? Same stuff. A was the antiderivative. F is the antiderivative. Same stuff.
Okay.
Okay? Let me give you the example that we just talked about.
So capital F of X is the same as saying A of X, so the same as area. Okay.
You remember this example, right? In fact, it was on the board. It's on the board right there. Here's what we'd say for this. We would say that f of x has an antiderivative of capital F of x, and capital F of x should be 1/3 or x cubed over 3. You okay with this so far? Is this the antiderivative or an antiderivative?
It's one of them.
It's one of many. It's one of many. This is an antiderivative. This is one antiderivative. I'm going to say anti-D. Why is it antiderivative? Why? Well, look at, if you take a derivative of this, does it not equal this? Why? Because the derivative with respect to x of this thing is this thing, which is f of x. That's why it works. This is all I'm saying here, folks. An antiderivative is this property. It says I take a derivative of it and it gives me a function. That's what it is. This is one of those. Are there more? There are many more. There are infinitely many more. I gave you another one. Another f of x would be x cubed over 3 minus 4. Is that another one? That's another. That's another one of those antiderivatives. That's why, in general, all of them will have this form. That's why we have the plus c. To say, okay, you know what? I'm kind of tired of writing every constant over here. I don't want to write minus 4. I don't want to write plus 3. I don't want to write plus whatever. I don't want to write 0, plus pi, minus 1/2. That's all garbage. I don't want to write that. I want to represent this. This represents all of the possible antiderivatives. Do you follow me on that? I can't have any other x's because that would alter the derivative. But constants don't, because when you take a derivative of a constant, it gives you 0. So this right here is all antiderivatives, the family of all antiderivatives.
And then there's also the integral.
I'll talk about that next time. This represents the family of all possible antiderivatives for f of x equals x squared. All possible antiderivatives will other functions have different antiderivatives? Of course they will. Of course they will. Other functions have different derivatives, so they will have other antiderivatives. What I will do next time is I will talk to you about what an integral is, what an integration is. It's basically you find out the same thing as doing antiderivative. So I'll show you some notation that will be where we continue. Our study of calculus has brought us to this point where we're not talking about derivatives so much anymore. In fact, we're basically doing the opposite of a derivative. From last time, we learned that if a function has an area under its curve, that's the area function, or in other words, that's the antiderivative. So basically, it's left to us to undo a function by pretending it's a derivative and saying, how can I reverse the process of taking a derivative? That process is called anti-differentiation, or finding the antiderivative. We left with this example. The antiderivative of x squared is 1/3 x cubed plus c. Why the plus c?
Because any constant.
Good. Yeah, the point of an antiderivative was if I take a derivative of it, in other words, the derivative of 1/3 x cubed plus c, it will give me back my original function. That's the idea of an antiderivative. I take a derivative of it, it gives me my original function back. Does that make sense to you? The plus c is there because, well, any constant's going to go away when I take a derivative. So that is basically a family of curves, a family of area curves, for which when I take a derivative of it, it gives me my original function back. Did you understand that from last time? That's basically a last time concept. Now, the process of finding the antiderivative is also known as integration. So when you hear the word integration or find the integral, it means find the antiderivative. Does that make sense to you? So antiderivative and integral, or antidifferentiation and integration, synonymous. They mean the same thing. This process, and I mean the process of finding the antiderivative, is also called integration. Let me show you something. Here's basically our definition in a nutshell. This is really it. Our definition of an antiderivative in a nutshell says, if I take the derivative, I even have it on the board already, if I take the derivative of my antiderivative, it gives me back my original function. Do you follow that? If I take the derivative of this thing, it must give me this thing. Do you follow? Okay. There's another way that we're going to write this. You see, this is kind of confusing because this doesn't let us go from here to here, right? This basically just says, if I do this thing, it will give me this thing. You follow? So we're going to write this a little bit differently. We're going to introduce a symbol called the integral. Remember, an integral means find the antiderivative, or perform integration, which is to find the antiderivative. So this and what I'm about to write mean exactly the same thing. This says if I take a derivative of the antiderivative, it gives my function. This says if I find the integral of my function, it will give me my antiderivative. Plus c. Because we don't know the constant, right? We talked about that already. It's a family of curves. By the way, is that c important, that constant? Yeah, that's 2 points on the test, right, every time. So you have to have the c. That represents, I don't know the exact integral as far as the constant, and it represents a family of curves for which I take a derivative and I get back my original. So this constant must be there. And this right here is called your indefinite integral. I think I referenced that before. I said it's indefinite, an indefinite integral, because you don't have any boundaries. You don't know where you're going. Basically, right now, all we're doing is finding the area function. It's very similar to this. You remember when I had to find derivatives? You ended with things in terms of x, right? So while that represented a slope, it wasn't an actual slope until you plug a number in. Do you follow me? This is the same thing. This is going to represent an area, but it's not an actual area until you plug something into it. And that's why it's called indefinite and not definite. Definite would be I'm able to plug numbers in and I get areas out. This is called the indefinite integral. The indefinite integral. And these things say exactly the same thing. Interchangeable. This one says take a derivative of your antiderivative, you get the function. This says find the integral of your function. What this says is this. It says find the antiderivative of this. Ah, there it is. That's the whole idea. Do you understand the notation we will do?
Why is the d and x there?
That's a good question. I'll get to that in just a second. That dx tells you what you're taking the integral with respect to. So what your variable has to be. So this dx right here says I'm taking this with respect to x. So that variable has to be x. If it's not, we can't do it. Does that make sense? It's got to be there. And we'll talk about this a little bit more as we go on and on. But basically, I want to get down the names, the notation. What's that called? That's integral symbol, or integral, that's right. What this means is find the antiderivative, or undo this as if it were a derivative of something. So give me some function that I can take a derivative of, and it will give me back what you start with. That's the whole idea right here. You okay with this so far? One note, this is also true. I hope this doesn't blow your mind, but I'm basically restating things a few different ways so that you see them a couple ways. Let's see if you can manage to do this. This is kind of critical thinking on a lower level. What's that stand for? Integral, or what else was it called? That's an antiderivative, right? What would you suppose would happen if I took a derivative of the antiderivative? What do you think it's going to give me?
Basic function.
The f of x. Yeah, this is true. That's a true statement as well. That dx, I'll make the note right here. That dx tells you what variable we are integrating with respect to. So this right here says which variable to integrate. For instance, that's why when we did this, now we can actually have symbols for it. Let's go ahead and try to do an example that we've had like probably 5 times, but just so you get the symbols down. We've actually done this problem. I think we've done it, I've had it on the board several times, but we've actually done it twice. The integral of x squared dx says, I want you to find the antiderivative of this function. What's the function? With respect to the variable x. That should match up. That has to match up for you to do it, okay? You can't do it if it doesn't, at least not with our single variable calculus that we're doing. So if we're doing the integral of x squared dx, we're going to find the antiderivative of x squared. What's the antiderivative of x squared? You actually already have that. Yeah, that's the 1/3. Or x cubed over 3 is fine. That doesn't quite do it yet. We also have to have, it's crucial, we've got to have that, plus c.
Oh, minus c, right? Can also minus c.
Well, if you had minus c, you could write that as plus negative c, right? So you're always going to write plus c. So c is just some arbitrary constant that can stand for anything. That's how you do most of these problems right now. You kind of find, it says antiderivative of this function with respect to that variable, and we know how to do at least one of them, right? But we don't know how to do any other ones. So right now what I'm going to do, I'm going to give you the basic integration table. Listen, if it doesn't fit in the basic integration table, you cannot do it right now. Okay? You can't create your own calculus here. If you do, you're better than Isaac Newton or Gottfried Leibniz, who invented this stuff way back in the day. That day was 1600s. So probably not going to happen. So don't invent this. Just follow the table. You do have to memorize it. I'm not going to put this on the board, but trust me, you will. The only tough ones are really the some of the trig ones that I'm going to give you right now. Some of the trig integrals are hard to memorize. But think of it this way. You already know the derivatives, right? We're just undoing them. So that's where all this stuff's going to come from. In fact, the table I'm about to give you is going to have the derivative and then the integral that's associated with it. You ready for it? Okay, so.
And this is called integration table?
Yeah, basic integration table.
I'm afraid to see what the advanced integration table would look like.
You know, there's a lot of them. There's a lot of integration tables.
What is that?
Yeah, most of the back of your book has just all those weird pages, right? And look at, what are all those, the curvy things? Someone had fun just scribbling. No, no, no. Those are integrals, and they mean something, right? They all have different formulas. By the way, this long, what is that thing? It's integral, but what does it look like? What letter? It's an S, and what we're going to come across in section 4.3 is that that's actually a sum. This is going to blow your mind. But remember how I told you that you can add all the rectangles together? That's what you're doing. It's a sum. It's a sum. Sum with a limit, basically. That's where the dx comes from. I'll show you all this. I'll make it very clear to you as we get there, but this is what we're doing. This is a way that you're adding all the infinite rectangles together and getting an area. You get it? Kind of cool. Kind of cool. It all makes sense in a little while. So basic integration table. Like I said, I'm going to start you off with the derivatives, and we're going to come up with the integrals that are corollaries of them. Because we know an integral undoes a derivative, right? So if we know the derivative, we should be able to somehow manage to get an integral out of that. So let me ask you this. What's the derivative? We'll start very simply. What's the derivative of x with respect to x?
1.
Very good. 1. Derivative of x is simply 1. Derivative of 2x would be 2. 4x would be 4. So the derivative of x is 1. What that means is this. Hopefully you find out what I'm going to do here. What's the integral of 1? What do you think? If the derivative of x is 1, the integral has to undo a derivative. That's what this says here. A derivative undoes an integral undoes a derivative. So they have to go in reverse. They're like inverse operations like division, multiplication, addition, subtraction, square and square root. Same idea. So if the derivative of x is 1, the integral of 1 is x. Sure. Why? Think about it. You're undoing this like it's a derivative, right? That means if you take a derivative of this thing, it should give you back that. Does it? Now we're missing something here. Plus c. You okay with this so far? Okay. You know, let's do this in general. What was the derivative of x to the r power? What do you do with that? What do you do? Okay. We add 1 to the... I'm sorry, I'm talking about derivatives here. Derivatives. How do you take a derivative of that?
Minus r multiplied by r.
Okay, multiply by r first. And then subtract 1 from the r. Yes? So like x cubed, you'd have 3x squared. So this would be r, x to the r minus 1. You follow me on that? Okay. That means that an integral should go in completely the reverse order. So where we took a derivative, we multiplied and then we subtracted, right? The reverse order of that is add and then divide by that new number. Does that make sense to you? So here we multiplied first and then we subtracted. For an integral that goes reverse, that means you're going to add and then divide. Add and then divide. So our integral says, I'm going to take, oops, not r, x. I'm going to take my x, I'm going to add 1, to that exponent, and what do you think? Am I going to divide by r minus 1, or r plus 1?
R plus 1.
Look what you do here. Look, we actually did this, right? How to get from here to here? You add 1, but you don't divide by 2. You divide by 3. Why? Because when you take a derivative of it, the 3 has to match up with that to go away. Right? So you're matching up the new exponent with that denominator. Do you follow that? So this isn't r, it's not r minus 1, it's r plus 1. Let's see. Basically, it says this in English. You add 1 to the exponent and divide by the new exponent. That's what that says in English. You add 1 to the exponent and divide by the new exponent.
Shouldn't that be rx to the r minus 1
Yeah.
instead
And
of
the integration.
This one?
Yeah.
Nope. No, I'm kind of changing it here. I don't want to have this over here. I don't want to do the same thing. I'm just kind of using this as a template to what you're doing. You're doing this in reverse, right? So this says you're multiplying and subtracting. This says you're adding and dividing by the new exponent. I don't want to make it look exactly the same in this case. I know you can, but it's going to give you back x to the r. What I want to give you is things so you can do this. X to the fifth. Right? Because your integrals aren't always going to look like this. This would be way too easy. they're not always going to look like that. Okay, not going to do that. Yeah, no, this, sure, that would be x to the fifth. Too easy. But what happens when you get something like this? Well, then you have to know, I'm going to add 1 to that. I'm going to divide by the new x number. I'm going to put a c. And that's the correct thing. So when I take a derivative of this, it will give me back that. Does that make sense to you? That's the way this has to work. So yeah, I know that these don't match up exactly. I know that. Also, one more thing I do have to mention before we go any further. Notice that sometimes you're going to have this. It's not even going to have a 1, because really we don't even write 1s most of the time in mathematics. So if ever you see the integral dx, you go, what's in there? It's a 1. It's a 1. Or integral of 2 dx. Well, that would be 2x. But this, that stands for the 1.
Between the function what integrated and the dx, do you need parentheses there?
You don't? Not unless you have a few terms.
So
Sometimes
say
you'll
when you
have
have a
those.
polynomial in there or something.
You may or you may not. Oftentimes people don't put parentheses in there because it's implied that you're going from the integral to where it says dx.
Okay.
Which, by the way, you must have the dx. If you don't have that dx, I mean, that says you're not even integrating anymore. You don't have respect of which variable. You have to have that. It also closes off your integration. Does that make sense to you? It's kind of like the limit. Remember on the limits how you had to keep writing limit over and over and over and over again? If you didn't, I went, ha 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 ha. I laughed at you and I crossed out your papers and I burned them. Well, not really. But you had to have it. It's a must because that's the same idea. Are you okay with these so far? Some of you still don't like this. I know. You're used to it. If you don't like this, you're going to hate me on the next few. Whew. Not this one. Necessarily. Can you tell me what's the derivative of sine? Yes, very good. With that in mind, what's the integral of cosine?
Sin x plus c.
Sin x and plus c. Good. Yeah, very good. Do you feel okay with the integral of cosine? It's nice to think of these as I'm looking for the reverse of a derivative. I'm looking for something that when I take a derivative of it, it gives me back that thing. Do you follow? That's what you're trying to do. The reason why we have it this way is because if you take a derivative of this thing, you bring down r plus 1. Those cross out. You subtract 1 from the r plus 1 and you get r. That's why we have it written that way. How about some more? We have about 5 more to do.
There's 5 more trigonometric functions.
Please don't freak out with this, but I'm going to do this a little differently. I told her not to freak out. She did anyway. Jeez. The derivative of cosine. What's the derivative of cosine? Now, stop. Stop. I'm going to change this. Because you know what we don't want to do? We don't want to have derivatives, integrals of weird things. I don't want to know what the integral of negative sine x is. Because are you going to see negative sine x? No, probably not. You're going to see things like sine x. Do you get it? So I'm trying to make this thing, into the thing that I have over here. The only exception is that one. We don't write the -1. We have it in terms of r, so you see it more clearly. But this. If this gives you negatives, if the derivative of cosine gives you negative sine, what's the derivative of negative cosine give you?
Sin x.
Sine. Do you get me? That's what I want here. I don't want to know integral of negative sine, I want the integral of sine. That's why I changed that. Okay. You agreed that the derivative of negative cosine was positive sine. You agreed with that? So what's the integral of sine? Negative cosine. Are these going to take some practice to memorize? You betcha. Yeah, you betcha. You go in the reverse of derivatives. The opposite thing. Backwards.
Is that an opposite chain of everything?
No, you're lucky. There's no such thing as that. There's worse things.
Oh, no. And where did we get lucky at?
You don't learn in this class.
That's next semester.
It is.
You're not teaching 4B?
Okay, derivative of tan x. What's the derivative of tan x? Secant squared x. Okay, this should be pretty painless. Now this one's pretty easy. That means what's the integral of secant squared x? Tan x. I like the plus c, I heard it. Plus c. By the way, look at the board here real quick. Is it plus c like this?
No.
It's actually plus c like this, okay? Whatever the angle is, and then the plus c is the very, very end. Okay, 3 more. Well, let's see if you remember this one. Do you remember, and I'm going to change this, so don't get too excited yet, the derivative of cotangent?
Negative cosecant tangent. Negative cosecant cotangent.
Yes, negative cosecant. If tangent is secant, cotangent is cosecant. Yeah, that's squared. With a negative in front of it. Do you know what I'm going to do? I'll bet you can see it. It's the same thing I'm going to do over here, or the same thing I did over here. If I have cotangent, the derivative of cotangent gives me negative cosecant. What I want this to be is positive cosecant. So look what I can do. I can say, okay, if cotangent gives me negative cosecant, negative cotangent should give me positive cosecant squared. Are you still okay with that one? So I'm just moving negatives around, basically. And the reason is because I want to have my cosecant here to be positive. I don't want to have the negative cosecant in there. So what's the integral of cosecant squared x?
Negative cotangent.
Yeah, it's that. The integral has to undo that derivative.
Plus c, plus c.
Don't forget plus c. Two more. Secant. See, do you know secant? Someone on the right side. Do you know secant?
Secant.
Right side, right side, right side. Middle.
Secant tangent.
Yes. Yeah, some work to do. Right side. By the way, don't forget that x. It's not secant tangent x, it's secant x tangent x. Secant x times tangent x. So this is like this. Well, then what's the integral of secant x tangent x? Yeah, plus c. Which one am I forgetting? Plus c. If you know this one, you can pretty much figure this one out. It has a negative, but you can pretty much figure this one out. Yeah. Make flashcards up. Make flashcards up or something. You need these. You ever done flashcards before? There's these like cards that you flash. Not like blinker flash. You go on the back side and go, integral of secant tangent. Secant squared. Oh yeah, no. But make sure you have them. You also probably know what I'm going to do with this one. I don't want that negative there, I want the negative here. So if the derivative of cosecant gives you negative cosecant cotangent, then the derivative of negative cosecant gives you positive cosecant cotangent. So I'm going to change that around. That way I have the integral of cosecant x cotangent x dx, don't forget the dx, is negative cosecant x plus c. Isn't that fun? Isn't that cool? That's not too bad. Here's the bright side. Yeah, the bad side is this stuff sucks, right? I mean, this is hard to memorize, especially these four. These ones, not so bad. This is easy. This is easy. This is pretty easy because you deal with sine and cosine more often. This is okay. You know where people mess up. I guarantee you, you know where people mess up. Where you're going to mess up if you make a mistake. Where are you going to mess up?
Sine.
The signs. The sign, positive, negative, all the time. Because you're used to doing this. Just think about it. Think about it for a second. If the derivative of sine is cosine, the integral of sine you can't have the same thing both ways, right? The derivative of sine can't be cosine, and the integral of sine be cosine. Something has to change there. So here, the integral of sine, yeah, it's negative cosine. The reason is the derivative of cosine would give you negative sine, so the derivative of negative cosine would give you positive sine. You can think through it, but it's harder. People make most of the mistakes with sines, almost all the time. That's where all of it happens, especially that stuff. The bright side is, if it does not fit in this table, you can't do it right now. I'm going to show you one exception to that. One, just one. It's called integration by substitution. It's very easy. But again, what you get must fit in this table. If it doesn't fit, you can't do it. That's a good thing and a bad thing. Good thing because if it's out of our realm, you won't even come up with it, so you know you're going to have an answer. It's a bad thing because sometimes it's hard to make things fit. And so I'm going to show you some examples on this, but memorize these tables. I'm going to need to erase them. Are there any questions before we begin? Did you see how I got all of them? Basically just undoing derivatives is the whole idea of integrals. That's why it's called an antiderivative.
So those are going to be all the answers on our test and write down the board.
No.
No. Nice try.
Good try. Okay, I'm not giving you that one anymore. We dealt with that one 4 times. How about this one? The integral of x to the 4th dx. Does it fit your table?
Yes.
That's something to a power that fits your table. That's why I gave it to you this way. What are you going to do with this? Subtract or add? Multiply or divide? You're basically then doing a derivative. So instead of multiplying and then subtracting, you are adding and then dividing. So on our answer here, you're going to have x to the what? 5. Yes, that's right. You add 1. You add. And then divide by what?
5. Is it okay if we write as 1/5 x?
Sure. Yeah, in fact, I think your book often writes it as 1/5 x. You know it's the same thing though, right? X to the 5th over 5 or 1/5 x. And then, don't you forget that plus c. Ooh, let's try this one. Notice how I have to always write my dx, right? If you don't have that, it's not a good way to write an integral. You're missing something. Does that fit your table? Not quite. Here's what you can't do. You can't do this. You can't go, yay.
Plus C.
Not so much. Plus C. Oh yeah, now you're right. No problem now. Yeah. Could you break the quotient rule by just doing the derivative of the top, or the derivative of the top and derivative of the bottom?
No.
You can't do that. You can't do that. You had a quotient rule for that, right? Well, we don't have things like the quotient rule, but note, this is what I said to you earlier, it must fit your table precisely. I don't have anything in my table, nothing. There's nothing 1 over that. Is there?
Make it negative.
Make it a negative. Make it x to the negative 3. That would fit my table. This, no. Oh dear. This is true. Yes. Make it fit your table. That's what you got to do. So x to the negative 3 hey, now we have x to some power. Now we can do it. Just be careful when I say add, I do mean add. I don't mean get x to the negative 4, because that would be subtracting, right? If we're adding to that, you're going to get x to the negative 2. Very good. Over what?
Negative 1/2. Or
Over
Negative.
negative 2. That's what you're getting, over negative 2. Yes, of course, because you take it over your new exponent, negative 2 plus c. You might make this a little bit prettier. You can do negative 1/2. You can do negative 1 over 2x squared plus c, which is probably the most appropriate way to write that. Do you see that? This goes down, that stays there, negative goes up. You okay with this so far?
Any one of those would be acceptable.
This is most acceptable. Yeah.
I like to be a little unacceptable sometimes.
Now, by the way, could you check your work? Hey, what checks your work?
Derivative.
Duh. I mean, yeah. You should never get the wrong answer. You can always check your work. Unless you do it really hard intervals. But most of the time, you can check your work. Right? All the time you can. It just gets more difficult. But here with these easy ones, man, you should never get one wrong. You shouldn't ever get one wrong.
We will somehow.
Some of you will. Yeah.
Somehow we will find a way.
Okay, is that in your table? Make it fit your table. What do you do? So we got it. X to the 1/2. What do you do with the exponent? You add or subtract? With integrals, you add. So we're going to get, what's 1 plus 1/2? Is it 1? It's 3. So x to the 3/2 over, this is why I do the over so you can really see this, over 3/2, right? Over 3/2. You got me? So that's x to the 3/2 over 1 divided by 3/2. If you, I'm never going to do this again, but you can see it this way. X to the 3/2 over 1 over 3/2. Reciprocate and multiply. What you end up getting is 2x to the 3/2 over 3. I ran out of room, sorry. Plus c. You notice a couple things about this. Firstly, did I put the plus c right when I did the problem? Not really. We only need it at the very end, just the very end. You can ignore it as long as you don't forget about it altogether. Put it at the very end. Also, could you check this with the derivative? Well, let's see. Derivative says you multiply by that. Hey, there goes the 2/3. Subtract 1 from it. There's the 1/2. The c's gone because c's a constant, right? Derivative of a constant is 0. That's the correct answer. That's what we need to be getting. Ready for one more? I'm not supposed to do this one. Oh, good. Mm-hmm. What do you do first? Yes. Now play along. When you do this, you get, I'm going to do every step for you. You get x to the -1 plus 1 over -1 plus 1, right? You get x to the 0 over 0. You get 1, oh crap. You get oh crap. Why oh crap? You can't. So when you see this, can you actually do it? This right here is something out of the realm of this class. We do late transcendentals. We do functions like this later in 4B, which you're going to get this. I'll give you a little hint. What this gives you is actually, the integral of this is actually ln x. That's the integral of 1 over x. So when you see this, when you see 1 over x, you can't do it in this class. Right? You're not going to be able to do it here. I just wanted you to see it, that, yeah, that power rule only works if your exponent is not -1. If it is -1, you divide by a new exponent that is 0, and you can't do that. So this one's off the table for us. We can't do that one. This one, if you really want to know, this is, can't do that. You're familiar with ln, right? Natural log. It's ln x. Let's cover a couple properties before we go any further, and then we'll start just practicing some of these things, getting more and more used to taking an integral, finding those antiderivatives. The properties you're going to find out are very, very similar to the properties of derivatives. I'm just going to state them for you. You'll see them because they're exactly the same as derivatives. Like, oh yeah, that makes sense. First one is if you take, so properties. If you take and have an integral of a constant times some function that has an x in it, what do you think you can do with that constant? We can. And typically you see this a lot more with integrals. With derivatives, we didn't really do that. Remember? We said we could, but we ended up just multiplying. With integrals, you really do. You do it a lot. You can take a constant outside of your integral just like you could with a derivative. Possible. Yes. I'm going to put 2 and 3 together. Here's 2 and 3. 2 and 3 say, let's suppose that you had two functions being added together within your integral, like that. With derivatives, we could separate those, couldn't we? We could take the derivative of the first one plus the derivative of the second. That means here that works as well. You take the integral of the first one plus the integral of the second. What we couldn't split up was that, right? We still can't. We still can't do that. So you can't split up two integrals like that either. It's very much like derivatives because you're going backwards from a derivative. So you can't do that either. But this you can, and this is 2 and 3. This says you can take the integral of f of x dx plus with plus, minus for minus, g of x dx. It says I can take the integral piece by piece, basically. That's what that says. This one is not true. Not true. Still okay? Let me caution you about the C's. You know we have to have plus C's, right? Let me caution you on how to do the C's. I think I mentioned this just like 20 seconds ago, but I want to make sure you see an example. Let me give you a real quick example on this. If you had the integral of, let's just do 2x. Note that 2 is a constant. 2 I should be able to pull out in front of my integral, and I can. So this would be 2 times the integral of x. Remember how I said your integral has to fit your integration table? This does. What's the integral of x?
1.
Oh dear. Are we doing derivatives? Think. X squared over 2 is correct. Yes. Oh my gosh, I erased the integration table and y'all forget. I imagine.
You erased our brain.
I did. 2 x squared over 2 plus c. Does that make sense to you? You have the 2, you have the x squared over 2 plus c. Now, for those of you who have written it like this, for those people who think, oh, I need the plus c immediately, well, that gets confusing because what are you supposed to do? Do this? If you do that, what do you get? What do you really get? You get x squared, right? You get x squared.
Plus 2c.
However, what is plus 2c?
2 times.
2 times a what? 2 times, which gives you another.
Constant.
So does it matter that's 2c?
No.
No. Just c. That's why I said you have options. You can put the plus c immediately and be careful on it, or really just ignore it and put it at the very end of your problem. Can you do that for me? Here's another example about why this is kind of useful. I'll give you one more. Integral of 1 plus x dx. Can I split that up? Yes, no. That's the integral of 1 dx plus the integral of x dx. Here's what I mean about the c's. Just watch. Just watch. Okay, watch for a second. You write down later. The integral of 1 dx is x. True? If you said, oh, x plus c, you have to call it c1. This is going to be another constant. Plus, this is x squared over 2. Yes, we just did that. Plus c2. But then when you add them together, you get x plus c1 plus x squared over 2 plus c2, and you get x plus x squared over 2 plus c1 plus c2 by recommuting those things. Can you follow that? How much is c1 plus c2?
Constant plus constant, which we go for a
It's
constant.
another constant. Who cares what it is? It's going to be a constant. Does that make sense? So here, ignore the c1 and the c2. That's too hard to deal with. So basically, you'd have x plus x squared over 2 plus just c. It's just going to be a constant there. You're not adding together different c's and go, oh, crazy. It stands for any constant. So any constant could be c1 plus c2, but who cares?
So no matter how many integrals you have to line up, you just always end it with plus c.
You're going to have 1 plus c at the very end of your problem.
No matter
That's
what.
for indefinite integrals, no matter what. Okay. Now, one last thing. You remember how with derivatives, when I said, I want you to take the derivative of 2x squared, don't write this down, just watch, minus 4x plus 3. You didn't split that up, did you?
No.
You did 4x minus 4, and then zeros for derivatives. You can do the same thing with integrals. So here, could you split it up? Yes, you can. But could you get directly from here to here? Sure, you can. What's the integral of 1? What's the integral of x? X squared over 2. Where's the c coming from? You need a plus c. That's the same thing. I'm just saying that this is possible, just like I did with derivatives. This is possible, therefore you can go directly from here to here. You with me on that? What you can't do is this, again, you can't break the multiplication thing. You can't do integral of this times integral, that doesn't work. So when you have functions of x multiplied together, like this one,
Is there a special rule for that?
nope. Yeah, kind of. You can go directly from there to there. But something like this. What you could not do. You can't take the integral of this thing times the integral of that thing. That doesn't work. Doesn't work at all. What could you do? You could distribute. That would save all your problems, right? Now, you couldn't do that with that, all right? You can't do that. That wouldn't be possible. But I'm going to show you ways that on certain cases, like this one, I will show you how to do that particular example, all right? Some integrals are going to be off limits for us in this class. You get that in 4B. But a lot of them we're going to be able to do, but they must absolutely, with all else, with everything else failing, fit your integration table. They have to do that. So whether you need to distribute, whether you need to do something else with it, make it fit your table somehow, that's the only way this stuff works. Still okay? Shall we try a couple more and then call it a day? So that one we can't do yet. Integral of 4 cosine x dx. Let's see, what do you do with the 4?
Move it outside down.
Constants, we often do that, we really do. We say this is 4 times the integral of cosine x dx. That makes it fit our table, that's easier to recognize. Just don't forget about the 4. You got the 4. The 4's going to be there being multiplied by whatever you get next. What do we get next? What's the integral of cosine? Think about it before you answer. What's the integral of cosine x dx? Negative or positive? You should answer it this way. When you take a derivative of it, does it give you positive cosine x? Because that's what you're looking for. Was it sine x or negative sine x? Positive sine x. Remember, you can always check your work. No sense in getting the wrong answer here. The derivative of sine x is cosine, positive cosine. That works. That's what you want to get out of that. Okay. If you ever see parentheses around that, it doesn't really mean anything special. It just means you're taking the integral of the entire thing. All right, so this basically means the same thing as what I've been writing as this. Those parentheses just say everything's included in that. Do you see the difference there? There's really no... It's just grouping them. It's just saying this integral of the entire thing. It's not making anything special, no special multiplication or whatnot. Can you take the integral of x? Do that now on your own. Take the integral of x. Write that out. Just do it. You don't have to say it, just write it out. Integral of x is 1. True or false? What is it? You can write 1/2 x squared, or you can do x squared over 2. Plus, because we have a plus. Hey, we can separate them by addition. That means we can just do them piece by piece if they're being added or subtracted. Not multiplied, divided, but added, subtracted. Integral of x squared, what's that? I'm going to assume your mumblings were x cubed over 3. I think some of you said that, actually. And then what? No 2 c's, just plus c. That's all we want. That's pretty much it. How many people understand the basic idea of integrals? We're going to practice a whole lot more of this. I'll show you things we can and can't do next time. All right, so we're still doing some integrals, our anti-differentiation, going backwards from a derivative, backwards of what a derivative is. So let's go ahead and talk about that problem. That's what we're going to start off with, so you get our brains a little motivated. When it says an integral, that means find the antiderivative of whatever function in terms of this variable that I give you. So this says with respect to x, so our function has to be in terms of x. That's what we're integrating with respect to. So when we have 2x to the 5th minus 3x squared plus 4x minus 8, do I have to necessarily split that up term by term, or can I just find the integral of each little piece? With addition, subtraction, each little piece is fine. With multiplication, division, each little piece is not fine. We knew that integrals, just like derivatives, were separable by addition and subtraction. What that says is it allows you to do the integral of this piece, minus the integral of this piece, plus the integral of this piece, minus the integral of this piece, and then jam it all back together. You follow me on that? Let's go ahead, let's take this integral. What's the integral of 2x to the 5th? Can you tell me?
X to the 10th over 10.
Oh, no, not quite. Okay. Is the 2 still going to be there?
Well, you're going to reduce it out.
Okay, but is it going to be there when we start? Let's do that.
Okay.
This little piece. That 2 is a constant, right? When we take an integral, just like a derivative, the constant doesn't do much. In fact, if you were to break this up, you'd write your constant in front of your integral. Now, we're a little beyond that. We just do the integral as we did derivatives. We look at it, we do it piece by piece. So we say this is a 2. No problem. The x to the 5th, what's the x to the 5th become? X to the 4th or x to the 6th? Why 6th? Yeah. Over what?
6.
Yes. The new exponent is what you divide by. So we're going to get 2x to the 6th over 6 before we start simplifying. Are you following me on this so far? Again, you know what? It's probably useful to check this with a derivative at some point. If you took a derivative here, notice you're going to get 2x to the 5th. That's nice. You can check that. Make sure you have these right. Minus. Let's see the next piece. How about 3x squared? What's the integral of 3x squared? Okay, I like the way you said 3x to the 3rd over 3, because I'm going to simplify it in a moment. I'm going to write out the integrals just like they are, and then I'll simplify it just a bit. We okay so far? Plus what? Very good. You sound like my little drums today. 4x squared over 2. That's good. No emotion, but at least you're right. Fantastic. And then the minus 8 goes to 0, right? Because all constants go to... Oh, wait.
No.
When do constants go to 0? We're not doing derivatives. We're going backwards of that. So if a constant goes to 0 in a derivative, a constant goes with an x in an integral. So this goes minus 8 x. And that's it, right?
Over 1.
Over 1, I guess you could if you really wanted to. We don't need to show the over 1. But we are missing something very crucial.
Plus C.
Yeah, plus C is important. Again, what we're finding is a family of curves. A family of area curves, basically, from this. This is a family of all the curves such that when I take a derivative of it, it'll give me that. That's what we're talking about. You with me? By the way, if you take a derivative of this, will it give you that? Certainly. That's how we found this in the first place. That's why it's called the antiderivative. Now we're going to simplify a little bit. Some of you already told me this is 1/3 x to the 6th or x to the 6th over 3. Minus x cubed plus 2x squared minus 8x plus c. That is our integral. By show of hands, how many feel okay with this example? Kind of a basic example, right? Not too bad. I am going to show you some ones that you do have to do some work to. This one was nice because everything fit in our integration table right away. There are going to be some cases where that is not true. So we'll take. Would you like to see a couple of those examples? Okay. I think I gave you one last time that I'm not going to give you again, but I want to talk about it. Like that. We're not going to go all the way through this, but I want you to look at it. I gave you an example similar to that before. Can I just take an integral of this and an integral of this and multiply it together? Does that work? No. No, it only works separation by addition, subtraction. So, if I gave you this problem, what's the only way you have to do it right now? Distribute, make it look like this, and then you can do it. Does that make sense? You get like x to the 4th minus 5x squared plus 6. At least I hope so. I guess we can go all the way through. It's not that hard. But once you do you see the distribution there? Once you distribute, then you can take an integral. It's fairly easy after that. And that's what we're going to get. You okay on that one? So even if it doesn't look exactly like this, sometimes you can make it look like that by some distribution or some working with our fractions or manipulating some trig functions. We'll see that on the next ones. Are there any questions on this particular one? You guys alive today out there? Yes, okay. You're freaking me out. Do you remember me telling you that with your integrals, they absolutely must be exactly like on an integration table, or otherwise you cannot do it? That was not a lie. Okay, that's a true statement. So when I give you something like this, is that right there on your integration table? Then you can't do it the way it is. That means you have to manipulate it somehow. So when we look at this, what we're constantly trying to do is somehow figure a way to make this fit something on our integration table. That's the idea. These fit because they're polynomials. They're very easy to do. With trig functions, they got to match exactly. Well, you can't even be missing a little piece. We got to make them match up. So when you're dealing with things like this, it's often nice to break them up and see if you can manipulate around those trigonometric identities that you know and love. Maybe not love, but at least hopefully know. So for instance, let me give you a method on how to do some of these. One method would be, okay, let's say I split this up as 1 over sine x times cosine x over sine x. Are we okay on that one? Do you see it's legal to do? That's still cosine x over sine squared x, right? Now, why am I doing this? Well, firstly, because I'm pretty good at it, right? I know what this is going to be. But secondly, because I'm trying to get some other identity, because I know right now, cosine x over sine squared x, that over, do you see the over? That's nowhere to be found in your integration table, is there? There's no over. There's no fraction on your integration table anywhere, right? But what there is when you have something over sine and something over sine, you can oftentimes translate those into some other trig identities that might be on your integration table. So if you see an over, that's not a good thing for you right now. Okay, if you see an over right now, and later on I'll show you some other ways to go about doing this. Method one is, well, manipulate it into something you can work with. If you have something over sine, translate that back into a different trig function and then see what you have. What is 1 over sine? That's cosecant times, not tan.
Oh,
I'm pretty sure I gave you a nice one. If you haven't memorized that integration table, which I'm guessing you probably haven't in one day, why don't you take out your notes and look at it? Find the integral of cosecant cotangent. Cosecant x, cotangent x.
negative cosecant plus.
I want you all to find it. Get it in your, at least read it on your own. Find it. Reading something like that reinforces the idea even more besides just hearing it from somebody. So I want you to find it, look at it, and identify that they're right. I wrote them on the board.
Oh.
They're on the video. And they're also in your book. Did you all find it? Okay, so cosecant cotangent, I gave you a nice one because that's actually in there. If it wasn't, you wouldn't be able to do it. It has to be there. It has to. So that means you're going to manipulate these around until you find something that's exactly in your table, which I guess is kind of a nice thing, isn't it? If it's not there, you can't do it. Sometimes making it get there is fairly part of those. So this one, you said negative cosecant? X. Yes? Plus, very good. Feel okay with that one? Let's take a look at one more that I want you to see. Now it looks kind of nasty, but firstly, before you go any further, can you tell me something that is wrong with that integral right now?
It's with respect to x, but the variable's t.
Say that louder for me.
It's with respect to x, but the variable's t.
Do you see the discrepancy? If I'm asking you to take an integral with respect to t, I'm sorry, with respect to x, my variables have to be x. If my variables are t, that needs to be a t. If it's not, then you can't do it the way this is. All right? You have to have that in the same variable. So that's correct. That's fine. Don't forget your dt. That's important. Now, oh, OMG. Is that in my integration table? Heavens no. No, we don't have anything over anything in our integration table, so this can't possibly be. Now, one more question. Can I take the integral of this, the integral of this, and the integral of that? Does that work? No. Is there a quotient rule for integration? No. Make it fit. Make it fit in your integration table. So manipulate this somehow. Someone on the right-hand side of the room, give me an idea about how I can manipulate this to make it look maybe better. Say what?
T to the negative 4.
Okay, I can't quite just move that up there whenever I want to because it's being subtracted, but you're on the right track. I like the thought.
Can you factor stuff out?
Factor stuff? What do you mean factor stuff out? Wait, say that again?
Break it apart.
When you deal with things sometimes, it's often nice, occasionally, to be able to do this to it. Right? Which is a true statement. Notice that if I do that, and this is a very big hint, whenever you have one term on the denominator, that's possible, right? Two terms, not possible. But one term, you can always do that. Do you see what I'm talking about? If you break up each individual numerator term over the denominator factor, you get all these different fractions, each of which will be simplifiable. Each of one. So yeah, absolutely correct. Let's make this, I'll show you every step here. Let's make this t squared over t to the 4th minus 2t to the 4th over t to the 4th, and there's still a dt. By the way, try not to overthink these things. Do the simplest thing that will work, not the hardest thing. Do the simplest thing that will work. That's the simplest thing that's going to work. Why is that the simplest thing that's going to work? I don't know, you tell me. Can you simplify each of those fractions? Absolutely, and they're not going to have any denominators anymore. So when I have t squared over t to the 4th, well, I know that we subtract exponents when I divide like bases. So that's going to give you t squared or t to the negative 2?
Negative 2.
Minus, how about the last one? What was it?
2.
Oh, that's great. I love that. Does this look a whole lot better than that one? Yeah, for sure, because this fits our table, and that's what we needed it to do. So let's do the integral of t to the negative 2 minus 2. Do it on your own, see what you get out of that, okay? I'm putting a dot, 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 because I'm going to add more to that question after we solve the first part. Before we get there, let's look at this part. We're going to do the integral of t to the negative 2 minus 2. Well, hopefully you got t to the, is it negative 3 or negative 1?
Negative 1.
You're adding 1 to it. Negative 2 plus 1 is negative 1 over negative 1. Did you make it that far? Minus what? 2t. 2t. Cool. Maybe plus c at the end. Now you can hold off at the plus c until the very last step if you want to, as long as you have the plus c. We found out that plus c, that's a constant. It really doesn't matter where you have it, as long as you have it at the end. It's just a constant. Now I will make this a little prettier. I'm going to move that exponent to the denominator. That'll be negative 1 over t minus 2t plus c.
Whenever we have negative variables, we should at the end move them down. Or negative exponents.
Yeah, typically yes. Are there cases where you don't? Yeah, there are, but typically yeah. Would you raise your hand if you got that one? Good for you, fantastic. Integrals versus derivatives so far, easy or harder?
Harder.
Harder
Harder now.
You'll get used to it. Now let's look at the next question. Find the equation of a curve. Well, you better get used to it. Find the equation of a curve such that the slope at each point is x squared. Let's think about what this means. Find the equation of a curve such that the slope at each point, is x squared. What gives you the slope of an equation? So basically it asks this. Give me an equation so that when I take a derivative of it, the derivative is x squared. Do you got me? That's basically asking for the antiderivative. That's what this question asks. It says, give me an equation so that when I take a derivative of it, when I get the slope at any point, that's a derivative. That's going to give me x squared. So this question says, okay, here's what you know. The slope at each point, recognize that's a derivative, right? The derivative means a slope at any point. That is dy dx. The slope equals x squared. True? The slope equals x squared. How do you undo that? Well, how do I find the equation that's going to give me that? Take an integral of x squared dx. You're going to notice some weird things, and this is kind of the way it works. It's interesting. I can show it to you a little bit later where all these symbols come from, but do you notice something? This is weird. But you know something about this? If I treat this like a variable and I multiply, I get dy equals x squared dx. Do you see where the dx is? Interesting, huh? If I want to undo a derivative, an integral undoes that. An integral undoes that on both sides. Integral of dy is y. Aha! Look at that. That's 1 dy, right? With respect to y. 1 dy with respect to y will give you y. Does that make sense to you? Did I lose you?
Yeah.
Do you remember I lost you?
A little bit. Yeah.
What was this?
I don't know.
No. What was this?
Oh, x.
Clearly. With respect to y, it is y.
Oh.
Equals the integral of x squared dx, which is exactly what we have right there. That's very interesting. It says undoing a derivative gives you an integral. Crazy? Crazy. Very cool. Anyway, that was a side note, beyond a little bit of the realm, but it's interesting how that works, right? Because some of you were asking, where's the dx, or maybe thought, where's the dx coming from? Why do we have that? It's from doing that, doing this idea. Undoing a derivative says, well, you work it this way, integral of 1 dy, that's y. Take an integral of both sides, you get an integral of x squared dx. Okie dokie, that works. Cool. Okay, now back onto this. Did you need that? Did you want me to write that back for you? You have it, right? Hey, it's on video. You can watch it again. What is the integral of x squared dx?
X to the third over 1/3 x to the third plus c.
So are you saying that that's the equation, right? That's the, what does that represent right there?
The family.
The family of curves, or function, the family of functions, I guess, function family. So that when I take a derivative of that, it's going to give me x squared. Is that true? For sure, any constant. Now, can I be specific? Can I give the equation in this terminology? Can I do that with this problem right now?
No, not right now.
Not right now, because I haven't been specific on the C. But if I change the problem just slightly, and here's what I'm going to add on to it. I'm going to say, let's find the equation of the curve such that the slope at each point is x squared, and that's why I add the dot, dot, dot. Given that it passes through the point 2, 1. Given that it passes through 2, 1. You know what? It doesn't make it any harder. It really doesn't. What this says right here is this family. All the x cubed families you can think of, right? It says any of them that are shifted up and down along the y-axis. Do you notice that? There's no other x's. This is just x cubes shifted up and down the y-axis. So where your y-intercept is different. What we're saying is now, choose a specific one and now tell me what it is. So the way to go about this is you say, all right, well, I know for a fact what we just found out is that y equals x cubed over 3 plus c. Not e, c. Right? That's what we have. Hey, do you have an x? Do you have a y? Plug them in, you're going to be able to find c. That gives you a specific equation. Not a family, but a specific equation. So when I plug in my 1 for y, my 2 for x, let's just solve for c. If I subtract 8/3 from both sides, what do we get? Negative 5/3, something like that? Yes, no?
Yes.
So when I do that, I get c equals negative 5/3. Can you see that down there? How do I finish up the problem? Well, it's not that hard. It's, you now know what c is, right? Here we were stuck without a c, so if I want to finish this off, I go back up to here, I say, all right, I know the equation, so that when I take the derivative of it, it gives me x squared when that happens, and it goes through this point, it's y equals x cubed over 3, and then what? That's right. Let's verify that for a second. Is this going to go through the point 2, 1? Sure, that's how we found c. When I take a derivative of this, does it give me x squared? Then this is the only equation, so that when I find the slope at each point, it's x squared and goes through this. That says it's not a family anymore. We've narrowed it down to one of these graphs. How many will feel okay with that one? That's the idea. This is very similar to what's called the initial value problem that we're going to study right now. We're going to talk about differential equations, just an introductory, not anything too drastic. They have a whole class on differential equations, right? I'm giving you like, you know when you get a new thing of ice cream and you open the lid and you get the ice cream on the top, you're like, oh, I better get that stuff because it melt real quick. You know that? The ice cream is differential equations. I'm giving you the stuff off the top. That's it. That's the skimmest tasting of ice cream. It's really sweet, but you get more of the good stuff in the actual class, okay?
It turns bitter.
I wouldn't turn bitter, it's fun.
Depends on what kind of ice cream you're talking about, sir. Depends on what you consider fun.
You ever had garlic flavored ice cream?
It's actually pretty good.
It's not like that. It's an acquired taste.
Garlic ice cream. I have a 3 semesters from there, so. I'm worried about it.
Yeah, so don't go home and say, oh, I learned all about differential equations. No, you didn't. All right, this is just a little teeny bit of it, but the idea is there. And we're starting with a basic idea. Let's pretend for a second, and this was basically it. I'm just kind of going to illustrate a little bit more. Let's pretend that I have a derivative that I know, like that. The idea is this. It's basically the same thing we were doing here. It's, can you find a function, an antiderivative, so that the derivative gives you this? The idea is, you know what, let me run it a different way. No, I don't think I need that there either. That'll make it easier for us. The idea is basically the same thing. If you know the derivative is f of x, can you find an antiderivative, basically, a function so that when I take the derivative of it, it gives me our original function back again? That's the idea. It's essentially the same as this. Let me show you how this works with what's called an initial value problem. After we do one basic example. Let's say that dy dx equals x to the fourth. Can you tell me what y equals? If the dy dx equals x to the fourth, can you tell me what y equals?
1/5 x to the 3.
That's what it would be. It's the same question here. Do you see how it's the same question? It's interesting, isn't it? Same thing I asked you here. Find me an equation so that the slope is this. That's what it says. Find me an equation so that the derivative is this. Instead of slope, I now have the word derivative. But it's the same idea because slope is a derivative. So here it says, well, I know that y is going to be the integral of x to the fourth dx. If you want that proof again, here's the proof again. Well, not even a proof, but here's a manipulation of these variable parts. If I separate them, I get dy equals x to the fourth dx, yes? To find y, I have to undo a derivative on both sides. Undoing a derivative is called an integral. The integral of 1 dy, I can put a 1 anywhere that I want to. The integral of 1 dy is y. The integral of x to the fourth dx is exactly what I have here. And that's why we're coming up with this. That's how you find the antiderivative. That's that. Does that make sense to you? Can you follow that? Have I blown your mind like a mind grenade? Are you with it?
Yeah.
All right. And Joe was right. X to the fifth over 5, or 1/5, x to the fifth plus c. Don't forget the plus c. So, what's a solution to a differential equation? It's actually not one. It's solutions to differential equations, just like we have solutions for a family of curves before I put this little piece into it. So the reason why I gave you this first is because this problem is a differential equation. It's asking the same concept. This right here is a differential equation. That's a family of curves. You got it? This right here would be an initial value condition, and that's what I'm going to introduce to you over here in the terms of differential equations. So both questions are the same. Give me the slope, give me the derivative. I'm sorry, give me the slope of, if the slope is this, find me a function so that the slope is what I've given you. Find me a function so that the derivative is what I've given you. It's the same exact question. Then I can add pieces onto it. Here's a condition that lets you solve for C. I'm going to give you an initial value problem that lets you solve for C. Would you like to see one of those?
Totally. That was funny.
I'll read that. I'll read that. This is basically when you only need one solution based on some initial condition. So this is a family of solutions right here. We're going to say, well, we only need one. We need something to fit a specific purpose, and that's what we're going to do here. So basically, here's an example. If you have dy dx equals 1 over 2x to the quantity cubed. An initial condition looks like this. It says y of some initial x value equals some initial y value. That's what that says. And here's what I'm going to give you. This looks pretty complicated, but here's what it says in real life. It'll give you like something, y of 1 is 0. That's what it would be. Can you tell me, what is your x coordinate here? What's your x? The 0 or the 1? The 1. The y would be the 0. This says when you plug in 1, you get out 0. Does that make sense to you? That's what that says. So can you first undo the derivative? Secondly, can you use this to solve for C? That's the two parts of our problem. So firstly, can you do that for me? Can you do that? Go for it. If the derivative of y is 1 over 2x to the third, we need to undo that derivative. That's the integral. That's the antiderivative idea. So what we want is to undo this thing. Tell me maybe the first thing that you would do. Make it fit the table.
Bring your bottom to the top.
You could. You'd have to be very careful with that. I'll show you both ways here, okay? Be very careful on how you handle this. Option 1 is bring the bottom to the top right now. Right? Right? Okay. Yes, that's right. If you do this, you can't take the integral yet. You cannot do it. What you would have to do is split that off, but you're going to get not 2 to the third, you're going to get 2 to the negative third over x to the negative, times x to the negative third dx. Do you see that? How it doesn't go to 8. That's actually 1/8. Do you see what I'm talking about? It's not 8, it's 1/8, so be careful on that. You get 1/8 x to the negative 3. That one you have to leave because that does fit your table. What can you do with the 1/8? Probably a good idea to do, right? We don't want to mess around with fractions too much because we create more fractions. It's easier if I write this as 1/8 x to the negative 3 dx. What is the integral of x to the negative 3 dx? Can you tell me?
X to the negative 2.
Negative 2, good. Out of line. Okay, well that is negative 1 over 16x squared. Do you see the negative 1 over 16x squared out of that? Can you make it that far? That's our algebra coming back at us. We're going to move our exponent down. Negative 2 times 8 is negative 16, but I'm going to put the negative on the top. Make that negative 1. And then, say it again. Very good. You'll find maybe the better way than moving that up to the top, maybe a little bit easier to see. Would you like to see that one? Different option here. Since you can't really do anything fancy yet, you don't know how to deal with parentheses at all, do you? There's been no such thing as parentheses. Maybe deal with that first and go, oh, well, this is 1 over 8x cubed. Yes? You follow? Then does the 8 move to the top? No. It's just the x to the third. That's the integral of 1/8 times x to the negative 3. And that gets you right to that step. Can you follow that one as well? So either way you want to do that, I really don't care. But sometimes it's easier to deal with those parentheses first off before you start moving all these pieces around, because you have to end up moving it back down to the denominator anyway. In either case, though, we're going to get negative 1 over 16x squared plus c. Tell me what I found. What is it? It is an integral, yes. It is an integral. A family of what?
Their functions.
Functions, works. Family of functions that does what for us? What does this family of functions do?
Solve your initial.
What do you mean solve for? Someone over here, tell me what does this family of functions, I said the wrong word, functions represent for us? Come on, help me out. We've had two ways to represent this. Way number one was, what's an integral or an antiderivative represent? Represents areas. We could consider that as an area because that's an integral, yes. In this context, this one, this is a family of curves such that when I take a derivative of it, it gives me that exact thing. Do you follow? That's what we're representing, a family of curves. How we find one specific curve or one specific function is we use the initial value. Now, this is basically the same idea as me giving you a point before, only I'm not giving you a point explicitly, I'm giving you a point right here like this. I'm not saying what x is, but you should know what x is. What is x here?
1.
And y is 0. It says y of 1 is 0. So what am I going to plug in? Well, let's see. It says the initial value for y, is 0. The initial value for x is 1 plus c. That lets you solve for c. In our case, we'll have 0 equals negative 1/16. This is kind of nice and easy. In this particular case, you add 1/16, and you get 1/16 equals c. Substitute that back in. And the exact equation that we're looking for to satisfy not only the differential equation, but the initial value is this. By show of hands, some of you feel okay with that one so far. Let's try one more just to make sure you really grasp this. I'll show you an example of how you can do it in actually real life, how this stuff works for you, and then we'll be done for the day. So last one, let's say dy dx is cosine x. Initial value is y of 0 equals 1. This one's going to be nice and quick for us. We're going to go quickly through it. If dy dx equals cosine x, y has to equal the integral of cosine x dx. We know that. We know that that is going to undo that derivative. So hey, can you tell me what's the integral of cosine? Think about it before you answer. I don't want anybody to answer in the first 2 seconds of what you think. Think of the integral of cosine x. Don't take it. What is it?
Sine plus c.
Sine or negative?
Positive.
Positive sign. Plus c. The plus c is important, right? Hey, if you forget the plus c, that initial value is meaningless, isn't it? You got to have that plus c to solve for something, so you had to have that. Do you see why it's sine, by the way? Take a derivative of sine, you're going to get cosine. Now we plug some numbers in. What do we plug in for the y in this case? That's my initial value. Is y 0 or is y 1? Which one?
1.
Y of 0 gives you 1. The of 0, that's your x. This would be like y of x. That's why I had it right here. Y of x equals y sub 0. So our x is 0, our y is 1. How much is sine of 0? Oh boy. Some of you are killing me today. How much is sine of 0?
It's 0.
It's definitely 0, yeah.
I was counting another.
1 equals c. No, you guys are right. 1 equals c. So our function that we were looking for is sine of x plus 1. Is it true that the derivative of this is going to still give you cosine x?
Yes.
Is it true that it goes with that initial value? Absolutely.
Being that x is 0, that means that it would be the y-intercept. So whenever you have the y-intercept, would c always come out to be the same?
It should, yes. Yeah, absolutely. Because you're plugging in 0 for x, it's got to be on that y-axis. Special case, I suppose. It's kind of nice. When you think about it, when you do an integral, right, you're always going to have something in terms of x or whatever your variable is, plus some c, which does not have your variable. So that naturally, if you're plugging in 0, everything else go away except for that. Would you like to see a real-life example? Are any of you in physics? Are any of you going to take physics? Oh, good. Do you know that you can build catapults?
Yes.
We're going to do a catapult example.
This is That's the main reason to take physics, to build a catapult.
That's what I would take it. I hated physics. I mean, I loved it. I loved it. My teacher was not very good. Not like the teachers we have here. They're good here. Is that how you spell catapult?
Sounds good to me.
You know they're originally intended to shoot cats. That's why it's called a catapult. Just kidding. But that would be pretty fun. I don't like cats.
Especially when you don't like
There's no cat I like. Now let's say you really suck at building a catapult. And you shoot it accidentally straight up in the air, right above your head. Is that a good thing?
No.
Not with a catapult.
Impossible.
It's possible. I've seen it happen with a really badly built catapult. Straight up in the air. So let's say it accidentally shoots straight up in the air with an initial velocity of 128 feet per second. I want to do a few things. I want to find the position function of this. For the projectile, basically. For the height. I want to know what the maximum height is. And I want to know when it's going to hit you in the head. Actually, when it hits the ground, so hit your foot. When will it land on your foot? When's it going to hit the ground? Oh, and let's say one more thing about this. Let's say that it actually shoots straight up with an initial velocity of 128 feet per second, and you're launching it off of a 16-foot platform. So you're up 16 feet, and then you launch it. So maybe not straight up, but just slightly over, so it's going to land on the ground, okay? Does that make sense to you? Or you move the platform real quick. Or maybe your catapult's 16 feet high, so when it starts throwing it, it's at 16 feet. So maybe the top of it launches it straight up. Something breaks, I don't know, you messed up. But it launches straight up from your huge catapult, and it's going up there, and you're like, oh crap, it's going to hit me. And so you just watch it and you count. Let's see when it's going to hit you. That's the idea here, because we would all do that, naturally. Let's talk about a few things that we should know. Firstly, let's call our position function S. That's typical for a position function. So S of t, according to time. The initial height. What is the height of this thing at t equals 0, right when you launch? So S of 0 is 16. Do you follow me on that? 16 feet. So right when it's launching, it's at 16 feet high because that's when it's letting go. What's the velocity?
120
Aha.
per second.
Yeah, that's exactly right. Going positive 120 feet per second. Now, here's a good question for you. What is velocity in relation to a position function? It's the what? The what? Velocity is the first. Do you remember that's the first derivative? So velocity is the first derivative of a position function. And it said initial velocity. So the initial velocity would be this, the first derivative at time 0. Because what's going to happen to your projectile? Is it going to stay at 128 feet per second forever?
No.
Probably not, because it's going into outer space. It's going to slow down immediately after you launch it out of the catapult, right? Gravity's going to affect it. We're not going to do wind resistance, but gravity's going to affect it. It's going to come up, and then it's going to come down. True? So the initial velocity at time 0 is 128 feet per second. I don't know if I spelled that right. I probably spelled it wrong. I'm not good at spelling. I think I have too many L's. Do I? Yeah. Acceleration. There we go. If you have acceleration like that, what's acceleration? I didn't say anything about acceleration, but think outside the box here, or actually think outside the globe.
It's going to be deaccelerating at 9.8 meters per second downward.
Now, we're very good. Did you hear what he said? He said it's going to be decelerating. It's still a form of acceleration, it's just in the reverse direction. So you're going to be accelerating negatively, because he's pulling it towards the ground. And he said 9.8 meters per second squared, which is true, but I'm talking about feet.
Oh.
So not 9.8. Do you know?
32?
Yes. Accelerate. Now, oh wait, another interesting question. What's acceleration as it relates to a position curve? Do you remember all this? Rates of change? Position function was a position. The first derivative gave you velocity. The second derivative gave you acceleration. So here's what we know. We know the second derivative actually that's going to be a constant, isn't it? The second derivative is negative 32 feet per second squared. Why is it a constant? Well, gravity doesn't change for us. So it's going to be pulling down a constant acceleration of negative 32 feet per second squared. How many people feel okay with our setup here? I'm going to show you what to do with this next time. We'll start here. We're going to continue talking about our catapult problem, and here's what we knew so far. We're launching from a catapult, and as the projectile leaves, the arm reaches up and reaches a maximum height of 16 feet, and then lets go, and this thing shoots straight up in the air because you built it wrong. It's going to have fallen on the ground right in front of you. Got it? It leaves the catapult with an initial velocity of 128 feet per second. Now, what's going to happen as soon as it leaves the catapult? What happens to that projectile?
Deceleration.
It starts slowing down. That's right. The velocity starts slowing down because gravity is affecting it. Now, what our goals here are to do is find the position function, that's position according to time. Find the maximum height. We can do that. We already know how to find maximum and minimum. And we're going to find out when the projectile will hit the ground. These two, this is going to be based off our position function. The maximum height, we're probably going to have our first derivative for that. You with me on this? So, what do we know initially with our problem? Well, we know that it's starting out at 16 feet. So, I said it starts from a height of 16 feet. That's because our catapult arm reaches a height of 16 feet and then lets go. So, the position at time equals 0 isn't 0. It's 16. It'd be like a pitcher throwing a ball. If the pitcher throws a ball, the ball doesn't start from 0, right? He's not going to go, that'd be the worst pitcher ever. He's going to throw it from up here, right? It starts from like 8 feet and then goes up. It's not going to start from the ground. Same thing with our catapult. So the position at 0 is 16 feet. The first derivative gives us velocity. So our initial velocity is 128 feet per second. That means that our initial velocity at 0, that's where we start right here, the velocity at 0 has to be 128 feet per second. Right when it's leaving, it's traveling at 128 feet per second straight up. Are you guys okay with that? All right. Now, acceleration. How we came with acceleration isn't magic. It's just something to do with the Earth's gravity. It says that acceleration is negative 32 feet per second squared. It means that gravity's pulling on everything with that acceleration. If you drop something from here, it's going to momentarily be at a velocity of 0, right when I drop it. And then gravity's going to take its effect and start moving and speed up and speed up and speed up and speed up until it hits the ground. You follow me? And that acceleration that's acting on it is a constant negative 32 feet per second squared. That means that the velocity changes at 32 feet per second every second. So it drops, after 1 second it'll be at negative 32 feet per second, then further and further and further and further and further. So do you see where we're getting all these numbers from? Now, the interesting thing is, using just this information, we're going to actually be able to work backwards and get all this stuff that we want to find. So let's try to work on that. First thing, right now what we know is basically we only know the second derivative. Notice how this is s prime of 0 and s of 0. We don't have a position function. We just know something about the position at 0. We don't have a velocity function. We just know something about the velocity at 0, at time equals 0. Are you with me on this? What we do know is the acceleration function. That's all we know, as a matter of fact. So if we know that we've got the second derivative, the acceleration function, in terms of t, can you explain to me how I could get maybe somewhere else besides that? Not taking a derivative, because that would give me a third derivative. I don't want that. But is there a way I can get from here to maybe one derivative higher? If we integrate the second derivative, it must give us the first derivative. Does that make sense? Well, it's kind of an interesting concept, and that's going to work for us. So here's what we know. S prime of t is going to be the integral of s double prime of t. The first derivative is the integral of the second derivative. And of course you need a dt. Are you okay with that one? All right. Now, why are we doing this again? Well, we don't have the velocity function. We just have the velocity at 0. So this is actually going to help us. Remember the initial value problems that we did earlier? This is basically what that is. So this says, all right, my first derivative is going to be the integral of whatever my second derivative was. In this case, it's just negative 32. Well, that's a pretty easy one. What's the integral of negative 32 dt? Can you tell me that?
Negative 32 t plus c.
T, why not x?
Because our variable is t.
Nah, it says t. Might as well use t. Negative 32t, oh wait, and you said what after that?
C.
Plus, is a c important?
Yes.
Okay. You know, a student asked me today, why is the c, why do you even need the c? And the answer is, well, if you take a derivative, let's say this, and this, and this, you don't have to write this down, just kind of watch it. If you took a derivative of all these things, what's the derivative here? What's the derivative here? What's the derivative here? Now, if you take the integral of each one of these are all the same, right? If you take the integral of all these things, you're going to get this. Right? Is it necessarily this one? No. I know that all three of these came from three different sources. So I can't take the integral of this and get one thing back again. It has to represent all of them. How we represent all of them is there could be a constant over there. That's where the plus c is coming from. That's why we have that. So anyway, we certainly do need the plus c. So good catch on that. Now tell me something I can do. Someone on the right-hand side of the room. Since we have s prime of t equals negative 32t plus c, tell me what I can do now. Okay, so initial velocity, hey, I have that. It says s prime of 0 equals 128. Where does the 0 go? Where's the 0 go? That stands for t, right? So s prime of t or s prime of 0 says, I know the first derivative equaled 128 when the t equals 0. Does that make sense to you? Are you sure? S prime of 0 equaled 128, right? So S prime of 0, the 0 meant the t, the 128 was the velocity at 0. This means the velocity at 0, that's 128. Can you solve for c? Yeah, this one's really nice. How much is c? So with a little substitution, we have that s prime of t is negative 32 t plus 128. Raise your hand if you feel okay with that so far. We now have a velocity function. It says velocity at any time t. Now here's something interesting. Which question can we answer right now? The first one, the second one, the third one? Can we answer the position function yet? We don't have that on the board. Can we answer the maximum height yet? Kind of, almost. Almost. We can get close to this one. We'll talk about that in a minute, but we're very close to this. Why? Where would a maximum occur? When the slope is 0. Do we have a formula for the slope? We do. It's right there. That's the slope, right? So when the... Think about that. Oh, I broke my pen. Stay. No, I can. Just recap, last time. When the catapult goes up and it stops, that would be where the velocity would equal 0, right? Then it's going to start moving negatively. So right where the velocity equals 0 is where we should have maximum. Or in other words, where the slope of the tangent line is 0. It's going to reach its peak and come back down. So that's going to be what we're going to be using in just a bit. Now, before we can actually find the maximum height, though, because we're going to have to plug that number in, we need to figure out the position function right after that. So let's go ahead and do that next part. If we know s prime of t, is there a way you can figure out s of t? Our same basic idea. S of t equals the integral of s prime of t. An integral will undo that derivative. So in order to go from our first derivative back to a position function, let's just take an integral of it. So that's how we write it. This is said, take the integral of the first derivative of your position function. This is the first derivative of your position function. I substitute that back in. I'm going to take an integral of this. Can y'all help me? What's the integral of negative 32t? What would you do?
Negative 16 t squared plus 128.
Okay, I'm going to do this a little bit longer, but yeah, you guys are right. I'm going to do negative 32t squared over 2, just so people can see where that's coming from. I'm going to take an integral, I'm adding 1 to the exponent, divided by the new exponent. Plus, don't forget about that 128. That doesn't go to 0. This is not a derivative, it's an integral. So 128t,
Plus C.
good, plus c. Now, of course, you guys are right. This is going to be negative 16t squared. In fact, if you've ever seen position functions for projectiles, they always have that negative 16t squared in front of it. Why? Why? Gravity. That's why. It's not magic. It's not magic. Someone actually did the work and said, oh yeah, if we're accelerating downward negative 32 feet per second squared, if I integrate that twice, I get a position function. That's going to be in my problem. Okay. Now, tell me, people on the left-hand side of the room, what would be the next step that I would do here?
Solve for C.
Good. Now,
Going
how?
back to your initial your initial function.
Since we have that, this is my position at 0. My position at 0 is 16. My position at 0 says plug in 0 to your t. This is my position at 0, and I knew that had to be equal to 16. It says if you plug in 0, look at this what it says. If you plug in 0, it's got to be equal to 16. Since I plugged in 0, it must be equal to 16. You okay with that? How much is C?
16.
Clearly, everything else goes to 0. So that means our position function is that. Should make sense. Says, think about this, diagnose this. What's this from? That part. What's that from?
Secondary.
Well, what is it from though? Where does it stem from? Well, I know it's integral, but
Gravity.
is it from the height? Is it from the velocity? Or is it from the gravity? Oh dear goodness.
Gravity.
Where did the negative 16 come from? It's from integrating this twice, right? I sure hope so. This part is from gravity. We just talked about that. Come on, people. Some of you are zoning out right now. Stop zoning out. Be with me. That's from gravity. You integrate negative 32, you get negative 32t. Integrate it again, you get negative 32t squared over 2. That's negative 16t squared. That's gravity. What's this? What's that come from? That's the initial height. In fact, if you plugged in time equals 0, you get 16, right? So you start from 16 feet. What's this from? That has to do with your initial velocity. When you start out, what are you at? So basically, I'm shooting something off and then letting gravity take its effect on that. And that's what that says. Feel okay where this stuff is coming from, at least.
Now, with any type of projectile problem like this, couldn't you just derive the answers from your initial values the same? I mean, there's a definite pattern between the value, your initial
Oh yeah,
values.
absolutely. All you need to know is your initial velocity, gravity,
Divide
and
that
your
by
initial
2.
height, and you can do basically the same thing with projectile functions. Now, of course, this doesn't take into account certain things.
Air
This
resistance.
doesn't take into account wind resistance, doesn't take into account like a propellant. So, you know how South Korea launched a rocket, or North Korea, sorry, launched a rocket yesterday and it went up and came down? Well, we couldn't model that exactly right because of wind resistance, because it probably didn't go straight up unless they're really just not very bright. Because from what I know, you don't launch rockets straight up. That would be stupid. But even if they did, right, we wouldn't be able to model it great because if they have some sort of propellant that's launching it, you have to take that into account. How the propellant's burning off, things like of that nature. This just basically says, I'm launching it and letting go. Or maybe the rocket took off and then the moment it took off, it just blasted real quick and but then it's not firing anymore. That would be a different story. This just has an initial velocity and then we let gravity take its course. There's a difference there. Now we're almost done. We have the first part, we've got this. we know that this is equal to negative 16t squared plus 128t plus c. In our case, c was 16. Okay, part 1 done. We can do part 2 and 3 at the same, well, not at the same time, but any time that we want. How would you do part 2? Let's talk about that. When would part 2 happen?
Well, you set it to 0.
Set what to 0?
Oh, your
The,
prime of t.
not the position, right?
No.
That would be a height. The first derivative, though, gives us the velocity. That says when it's 0, it's going to be at its peak. So if we set this equal to 0, (32t equals 128). What's t equal if you divide 128 by 32?
4.
Exactly 4? I love it. 4 what? Seconds, because t is a time. Seconds. So what's your maximum height? Is it 4?
No.
No, that's 4 seconds. How would you figure out your maximum height? Here's what you know. Your maximum height occurs after 4 seconds. So after 4 seconds, you're at the maximum point of your height, and then you start dropping. How would you figure out the maximum height? Plug it in where?
Your position.
The position function. Yeah, so that's why we had to figure out the position function first so that we could actually find the maximum height. We could have found out when it is the maximum height very easily. As soon as we had that, we could have done it. But to figure out the actual maximum height, you got to have something to plug it into. So maximum height occurs at 4 seconds. Can someone please plug that in for me into my position function and find out exactly how high we get? 784 feet? Someone else double check that for me? 784 feet, please. It's probably going to be a whole number.
Oh, crap. Yeah, 780.
So what this says is that your catapult you built is going to launch something from a height of 16 feet. It's going to go to 784 feet. That's after 4 seconds and then start dropping like a rock. When is it going to hit the ground?
Acceleration zero.
Acceleration is never 0. It's a constant.
Or when
Hey, let me ask you this question. What is the height when you hit the ground? You understand the height when you, if you fell on your face would be at 0 when you hit the ground, right? Right now my face is at 6 feet. And then it's going to go, and I'm going to get 0 feet off the ground. Does that make sense? Now, which one of these represents your height? Is it the position, the first derivative, or the second derivative?
Position.
Your position. So what this says is, when does this equal what number?
0.
When does it equal 0? This is actually a math an intermediate algebra question. We just did this today. I just taught this in another class today. It says, take this, set it equal to 0, solve for t. That's going to give you a time. In fact, it's a quadratic, right? It's going to give you 2 times. Do you see the 2 times that I'm talking about? One will be positive, one will be negative. You're going to take those 2 times. Which one is going to make sense for this problem? The positive t or the negative t? Oh, some of you guys are not with me today. What makes sense if you're going to hit the ground after some amount of time? A negative time? Can you launch a catapult and it hits backwards in time? That'd be pretty sweet. I'm sure North Korea would have loved that. I launched it and it hit them in the past. Ha 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 ha.
They'd have won the Korean War.
They would have won. Yeah, so that doesn't work. So what we're talking about is in your quadratic, when you do quadratic formula or whatever you want out of that thing, you're going to set this equal to 0.
It's not right. Yeah, 74 is not right. It's 2.
Why'd you both give me that then?
I forgot. Two people can't. It's negative. It's 270.
You didn't do negative 16. Oh, you
272. I kept. It's been driving me crazy. 272.
How do you calculus people make simple mistakes like that? I'll never get it. I don't understand.
Justin.
have good intentions, Leonard, come on.
So it's
You know what you matched up with good intentions and bad follow through? A bunch of crap. Bunch of crap. You have all the good intentions in the world. I intended to drive well when I was drunk. Perfectly did. I ran over 37 people, but fully intended to do well. Yeah. Okay, good intentions suck. Anyway, okay, so make a note on your paper. I don't do the math. I trust you guys. I should never trust you guys, apparently. 272 feet instead of 784. Make sure you have a negative. My goodness gracious, this is ridiculous. Anyway, I'm not going to do the rest of that for you. I'm going to trust you to make your own mistakes on that one. Use the quadratic formula. Figure out the time. One will be positive, one will be negative. The positive time works. The negative time says you launch a catapult and it lands in the past. That doesn't make any sense at all. Your positive time would be when it hits the ground. But you feel okay with our example? We got to move on. All right.